Building upon our non-uniform flow video, we have a channel transitioning from a mild to a steep slope. This creates two GVF profiles, one in the mild section and one in the steep section. To complete the analysis, we assume that the flow transition passes through the critical depth at the channel grade break. There are two methods to analyzing gradually varied flow: the direct step method and the standard step method. The direct step method is applied to prismatic channels, or channels where the geometry is fixed because it was built by man. In prismatic channels, the flow conditions are known at each section of the channel. In order to use this approach, we need to know the flow depths at the start and end of the GVF transition section. Therefore, what we do not know is the length between the start and end of the GVF section. For the standard step method, the channel section is irregular. An example of this would be a natural river geometry. Using this approach, we cut the channel at locations that are interesting to us so that we effectively know the length between the channel sections because we choose them. What we do not know with this approach are the flow conditions at each channel section. Because the direct step method applies best with prismatic channel sections, we will discuss how this is applied. The calculation can be summarized into this equation, which calculates the length of the transition as the change in energy between the starting and ending points of the transition divided by the channel slope minus the average friction slope. Let me just say, if you know what all these terms mean, then there is no need to continue watching this video. Carrying on, the change in energy is actually the change in specific energy, the velocity head plus the depth of flow at known locations. For example, in the schematic above, the gradually varied flow in the mild channel starts at the normal depth, then flows downstream until reaching the critical depth at the grade break. We just don't know how far this is, but we know that we are at normal depth at one end and the critical depth at the other. The friction slope is calculated by rearranging the terms in Manning's equation to solve for the slope term. Since we know the channel roughness and depth, we can calculate the velocity and the hydraulic radius. The average friction slope is just the average of the friction slopes calculated at the start and end of the transition. Applying this formula to the M2 curve above, we first divide the transition in the flow depth into multiple segments. The equation assumes that the change in energy between the start and end of the GVF is minimal. Therefore, to minimize the error in the calculations, we chop up the transition into 5 segments. Each of these segments corresponds to a specific location in the channel, each separated by a different change in length calculation. The total change in length between the normal depth and the critical depth is a summation of these smaller calculated lengths. Because of the number of calculations required, it is best to organize the calculations into a table where each of the input values are broken down into the respective parts. For example, the velocity head requires that you know the velocity, which is just the flow rate Q divided by the flow area at the specific segment. We can also calculate the hydraulic radius separately since it needs to be raised to 2/3 power. Using a table was the primary tool even before computerized spreadsheets were available because they made it easier for the engineer to audit their work for any mistakes. Checking one step is easier if it was recorded. This process is then repeated for the S2 profile, and we can calculate the length there as well.